Hello, everyone. Can everyone see me, hear me, and also see my slides? Especially for the folks on Zoom?
Yes.
Yes?
Yeah.
Okay, let's get started. Well, let me also get this so that I don't lose my voice. Hello, can folks hear me? Good, great. Okay, good morning. Good to see you all. And welcome to EECS 251B. Some of you may notice we made quite a few changes this semester, especially adding a bit more system component, really thinking about not only just circuit design, but really thinking about how we can optimize also at the system level. So with that, Vladimir did a really good overview of different system interconnect, especially different router design, different bus protocols. So now we're going to move a little bit higher up. I think really thinking about how we can actually leverage those interconnects so that we can build fully complex SoC, especially thinking from accelerator integration point of view. So before we get there, a lot of exciting news this week. Many of you probably already have heard Intel is actually pushing really hard to open up their foundry to not only just Intel's internal design, but also open up to a lot of external design. So Intel yesterday just announced their effort in really opening up Intel's foundry so that a lot of different designers, even with different IPs, different ISA, it doesn't need to be x86, can actually leverage Intel's foundry as a domestic fab here to build their interesting designs. As part of the effort, Intel actually also joined RISC-V Foundation. Very interesting move to actually facilitate really the RISC-V designs going through Intel's fab so that we can actually get even more interesting design and also a lot of different partners there, right? It doesn't have to be data center processor. There are a lot of low power embedded system processors are actually using RISC-V these days, and they can also actually leveraging here domestically Intel's foundry to fabricate their design. So a lot of interesting things here. We talk a lot about different IPs, right? That also resonates really well with the way we think about integration, right? So now when we think about ISAs, it's not only just x86, not just ARM, we also have RISC-V. And when we think about the accelerator, there are also different IPs that actually need to be integrated at the system level. And this kind of foundry opening up also very interesting so that anyone, if you have an interesting design, you can actually assemble different IP blocks together. There are also resources available for you to actually make your own design. So it's really interesting here domestically with Intel opening up, we will also see a lot more interesting designs with heterogeneous ISAs, heterogeneous accelerators being integrated together. So a lot of excitement here, and we'll see more actually when we think about not only just ISAs and also other IPs that can be potentially integrated. So with that, that actually works really well when we actually think about system integration. So last week, we have gone through our system interconnect module, really talking about what are the underlying protocols, what are the underlying circuit components that we can actually use. And today we are going to talk a little bit more about, okay, here are all those different connections, different interconnect, and then what are the different agents that we can actually integrate onto our system. And this is also a good opportunity for you to think about your project. Like you folks have actually gone through the chip yard for your lab 1 and also did a little bit chisel exercise for your lab 2. Now you see all the different ways that could potentially actually integrate different IPs onto your system, right? That could also be, now is a really good time to think about what your project would be. Of course, it can be, it's totally fine. You're interested on the circuit side. There are a lot of like very interesting circuit optimization there. At the same time, it will be really interesting to think about the system level implications and whether you can actually leverage the infrastructure that we have done with the chipyard and also other IPs so that you could also build some of the like very interesting system, maybe also go through Intel's foundry to actually get your design fabricated in the end. So it's a lot of interesting things can happen. So start thinking about your project, how what you would like to do, whether you want to do a solo project or work with a partner, now is a really good time because things haven't actually got too busy yet. And then we have seen a lot of other resources here at Berkeley available, and now, so it's a good time to think about projects. So with that, for this lecture, we'll be mostly focusing on the accelerator integration. I spent a lot of time really thinking about what would be a good way to introduce that. There are a lot of resources here available, but also sometimes also a little bit scattered. So here I'm actually using accelerator integration as a way to connect different components that you may already have heard here at Berkeley in thinking about different protocols, but many of them actually very useful when we actually think about this from a more integration point of view. So we'll start with the big picture of thinking about what are the different, why we actually care about integration, what are the different components are actually important, and more specifically, we'll dive down to actually two very important and also commonly used protocols for accelerator integration. One is the ROC protocol for tightly coupled accelerator, and the other is a tile-link protocol for actually more loosely coupled accelerators. Both are very useful. It may seem a little bit abstract when we first start, so I will actually introduce a couple examples and also with pointers where you can actually find in the open source repositories, like how they are actually used in the way we think about system design. So with that, let's get started. So accelerator integration, for this audience, we probably don't need to spend too much time on this, but we do see a range of different IPs actually showing up. And with a lot of this open source effort and also more different heterogeneous IP that we mentioned, it will be really interesting to think about future generation of SoCs with a range of different components like CPUs, GPUs, all the different kind of accelerators. And especially when we actually think about accelerator, you may actually already seen a lot of work, a lot of papers at ICC, like with all the different accelerator design, right? So of course, like novel architectural or circuit optimizations for individual accelerators are very important. At the same time, since we're talking about accelerator integration, one thing we like to highlight here is that accelerators, they also don't exist in isolation, right? So whenever we actually look at an SoC, of course, there are accelerators, but there are also other components like CPU, GPUs, and also shared memory, right? We see a lot of memory SRAM actually in today's SoC. All of them need to be actually connected. They need to talk to each other, communicate with each other. And with that, we actually need well-defined protocols and also management to facilitate this kind of communication. And if we look at like generations of mobile SoC in the past decade, right, we have actually been observing this kind of very steady increase of growing number of IPs actually being integrated. With that, it's even more important once we're actually adding our new novel ideas for individual IPs, but really thinking about how they actually fit in the big picture, how they actually interact with each other. So that's a topic today when we're actually thinking about not only just each individual IP designs, but how they actually put together, how they interact with CPUs and other components, especially shared memory. Just a little bit more when we think about mobile SoC, right? So we talk about a lot of accelerators. Many of them are actually running either concurrently or sequentially. There are a lot of interactions going on. So here is an interesting example from Google's SoC study, where they actually captures for, let's say, a very simple, like commonly used task, right? Recording a video. A range of different IPs are actually involved. Like CPU is doing manipulation, GPU is actually doing display, and also a lot of image pipeline doing compression, and also data is actually transferred, shared also through DRAM, so that all the different IPs actually interact with each other. There are a lot of memory traffic going on, and when we're actually going to talk about tile link, it is actually a way to specify how those links are supposed to interact with each other. What are the requirements there, how we actually meet different performance, bandwidth target, and also in some cases, maybe we also need coherence guarantee. So whether the protocol, the underlying protocol can actually provide that. So the setup here, especially when we actually get to tile link, is basically how those IPs actually interact with each other with the hypothesis or with the idea that they need to share data, right? So here, a good example, they actually work together, a lot of concurrency. Sometimes there's also this kind of pipeline fashion with a lot of data actually being shared across those IP. So those different protocols, we'll also talk briefly about some of the ARM-based AXI protocols, but many of those, the underlying assumption is that they need to share data and we want to facilitate data transfer in the end. So this, the one I mentioned is one example. The Google paper also shared a couple other scenarios. So we see, oh, CPU is always active, right? CPU is actually the management engine here doing a lot of manipulation. We'll also talk about ROC interface later, which is actually more how CPU and the accelerator interact with each other. So the CPU is always on doing a lot of manipulation, housekeeping, and depends on the task. Different accelerators are invoked. Some accelerators are always active, some are not. So this is also very task specific. So we think about accelerator integration, it also needs to be configurable, programmable, so that based on different tasks, they can actually have different ways of talking to each other. And some of them may even have like different performance metrics there. So we talk about SOC before we get to specific of different protocols, which can be like very specific. Before I get there, I like to just motivate the big picture a little bit more so that we understand what kind of system level interactions that we are considering here. And when we think about accelerators, right? So when we think about it, for example, we see a lot of deep learning accelerators these days, right? So when we think about SOC with deep learning accelerators, of course, there are like Gemini here. I'll talk also later where we use Gemini as an example to see how an accelerator actually can be integrated with ROC and tiling. So here with deep learning accelerators, we also have CPUs, our shared memory, just like a very simplified example of SOC with actually fewer number of blocks, right? When we have this kind of heterogeneous components, when they actually integrated together, there are a lot of system level interactions that we are interested. So what kind of system level interaction that we're interested? So it's, for example, a memory hierarchy is always important. When we look at even the diphoto these days, we actually see a lot of SRAM here and there, right? Like the global shared SRAM and also SRAM inside individual IP. So whenever like they actually need to access memory, and also you will remember the recording video that we saw earlier, right? The data is also passed through different IPs. So whenever they are sharing and also concurrency, multiple IPs are actually accessing memory together, there could be contention, right? How we arbitrate both the memory capacity and also memory bandwidth. How we handle actual coherence, right? If they actually accessing data at the same time, maybe even reading, maybe that's easier. But for example, if one is writing, the other one is reading, right? How do we actually guarantee it reads the up-to-date data instead of stale data, right? So this kind of even not only just performance, but the correctness guarantee is also very important when we think about system level interactions. The second dimension is really thinking about the virtual memory system, right? We need to expose accelerators to the programmer, right? So the programmers can actually interact with accelerators. One thing, the ROC-based accelerator, we'll talk a little bit more later, it actually provides a very easy way to expose the memory system to the accelerator. So with that, the benefit is that it's a lot easier to program, right? Instead of manually pinning your data to memory, right? We could actually leverage the CPU's virtual memory system, the page table walker, to actually get our physical address. So this becomes a lot easier. So when we think about accelerator integration, we look at all those protocols, right? Coherence is always very important. Bandwidth is also very important. And another thing to look at is actually how they handle like virtual memory system, right? Whether they support like memory address translation directly, or the programmers and the drivers actually need to actually ping the data specifically to the memory so that the accelerator actually access memory. We'll talk a little bit more later. There are also two different flavors, ways of designing accelerator. But besides the performance correctness issues that we discussed earlier, the virtual memory support is also very important. So finally, this is more like, so I think we're talking about accelerator integrations. There might be a tendency actually neglect the rest of the SOCs because we think accelerators are important, but always CPU is actually very important. The ROC interface that we're going to talk later is actually how CPU interact and also manage accelerators. So one thing to think about, so even some of the computation are actually not done on CPU. a lot of management, actually a lot of arbitration is actually still done on CPU. So CPU is still very important in that sense. And when we actually integrate accelerators, we also need to consider what kind of capabilities actually provided by CPU that can actually facilitate accelerator design. So here, just to set up the context, when we think about accelerators, performance issues are very important, right? How we guarantee bandwidth. Correctness is also very important, right? How we can actually guarantee that we always get correct, up-to-date data instead of stale data. And also programmability is also very important. How we interact with CPUs, how we actually support the virtual memory translation, so that we can actually get a programmable IP or system in the end. So with that, we are going to dive deep into two specific ways actually integrating accelerators. One is the tightly coupled accelerators through the ROC interface. The other is actually when more thinking about system level, thinking about memory mapped accelerator with a tile-link interface. Before I move on, any questions, comments, or things that you'd like to share for both folks on Zoom and also folks here in the room? Or your view of accelerators or SOCs or things that you are interested, curious, anything? Clear, simple, right? It's so straightforward, just doing Lego block assembly, right? Just stitch them together, right? What are we talking about here? Okay, well, it's basically like stitching the Lego blocks together, but we need to follow some rules here. So here are two examples of ways people use, especially inside the RISC-V based system. What are the things people are doing? So the first one we like to talk about is the ROC interface. So like we mentioned earlier, like the performance, correctness is always important. But ROC is really specialized the host CPU and accelerator integration. So this is really tightly coupled accelerators that can be actually integrated, almost like integrated as part of the pipeline of the CPUs, so that we can invoke those accelerators more like special instructions. So it's just a special instruction instead of executing on the CPU, but we actually invoke an accelerator to offload the computation there, right? So it's a custom co-processor interface within the RISC-V ecosystem. We'll see a couple examples later. The way I like to think about it is this is really for a tightly coupled accelerator, that there is something that interact with the CPU a lot. We like the benefit, like we'll talk about virtual memory later, and also very easy access to memory. So it's more like a special, but also a lot beefier functional unit, but instead of fit in the accelerator, we actually fit it in the co-processor or the ROC accelerator here, right? So here, I mentioned earlier, to invoke an accelerator is actually a lot easier. Instead of having a lot of drivers, requiring a lot of driver support when we think about accelerator, right? Here with ROC is really, we have a special, we'll talk about instruction format in a minute, but there are some instruction formats like what you have seen in 251A or 151, right? We'll talk about a lot of instructions. There's just a couple of those special instructions, and whenever the CPU sees that, it knows that, okay, those are actually not on my pipeline, but those are actually on my co-processor. Let me invoke that, right? It also has, so that's a command and response interface. It can also directly access L1, the D cache, right? So it's really like a functional unit, but not part of the pipeline, but with easy access to both the instruction pipeline and also the D cache, so that it can also benefit really from the fast latency from the L1 cache, right? So this is great. Like for your SHA-3 example, I guess your folks mostly is like just implementing the data path part, right? But I'll also mention later in the TripYard repo, if you are interested, you can also see how it is actually integrated into the TripYard, the Rocket SoC. It is actually basically using the ROC interface, right? Because it's great because I offload some computation there. It does a lot of heavy lifting doing the computation there and then return data to me, right? So this is a great way of using a very beefy functional unit that's actually very easy to program. Like I don't need to design a lot of drivers there. I don't need to manually manipulate the memory. I just have my special instruction ready and invoke them. So rock interface is really good for tightly coupled accelerator here. So we already hinted earlier, right? So here is rock is basically follow it's RISC-V instruction format, but has a couple like special setup so that whenever the processor sees this instruction combination, the bit patterns, it actually knows this is a rock instruction here. So the format is actually very similar. You can still remember what you did in 251A with the RISC-V project, right? The format is actually very similar. Actually, any guess? Very similar to which type of instruction? Looking at the opcode, we have RS1, RS2, and also return register, right? And func3 and func7, right? No volunteers? Too straightforward? Any guesses? Anyone online? We have 2 source registers and 1 destination register, which means R-type, exactly. This is basically the first, and your name is? Sarga? Yeah. Okay, good job. Yes, so this is basically R-type instruction, right? Very familiar. You don't have to memorize it, right? It's like, oh, we have 2 sources and 1 destination. Everything is registered, right? So R-type register, R-type instruction. So it's actually follow similar format, but instead of having actually func3, it actually have using those 3 bits as a more like valid bit. And I put here to actually specify whether the RISC-V pipeline is actually using. It's just like we have 3 registers, but sometimes those registers can be actually used by accelerator, right? So offloading value to accelerator, so accelerator is actually processing. So here, those 3 bits are more used as actually valid bits to see whether the core is actually using those registers. So by actually setting up those 3 bits and to see whether it's actually the core is using those registers for processing or accelerator. So this is a way actually passing values to accelerator, right? So we have 2 source registers. So those are actually offloaded to accelerator. So this is also a way to specify whether accelerators actually can use those registers or the destination register to return. So with that, we could actually have a different combination of operations actually passing data between CPUs and accelerators through registers, or passing data actually from memory to accelerators. So those instructions actually more act like load instruction there. Right, so whenever CPU see this, it know it's actually a custom rock instruction. So instead of processing here locally in part of the CPU pipeline, it invoked the accelerators to actually pass the data to accelerator to process it. We will not go to the details of different instruction encoding. So those are very important when we actually design. So that's what I mentioned earlier, right? So think about your project. If you actually want to design a rock accelerator, right? You have the freedom to actually choose your encoding, how your accelerator actually interpret those opcodes. So from a CPU point of view, is that whenever I see this, I send it to accelerator, right? And then it's up to accelerator to actually decide, okay, with this pattern, how I actually want to use it, to actually perform load or store, or do I actually do compute? So there are lots of things you can do actually inside the accelerator. So a fun exercise would actually be having some simple, like you have your SHA-3 and maybe has other like compute intensive like GCD module or any other modules, and think about if you want to actually use it as a tightly coupled accelerator, how you offload, how you design your rock instruction format to actually offload computation onto the accelerator. So those are the base interface. One thing I'd like to highlight here is actually the extended rock interface, which are actually very useful. This back to the virtual memory support that we mentioned earlier, right? To make programming easier. We'll also actually talk about like a very specific example later, how actually an accelerator design can actually use the rock interface to actually get the benefit of the virtual memory support. In particular, here we can actually leverage the page table walker inside our Rocket core here. So instead design everything from scratch, we actually think about the accelerator actually handle a lot of the virtual memory management. A benefit of the rock interface is that you can actually if you have a virtual in your TLB, if there are TLB miss, you can actually directly invoke the page table walker inside your core actually to do the address translation for you. So with this is actually very useful for accelerator design so that we actually don't need to manage the virtual memory system directly. And we can leverage a lot of facilities that already existed in the CPU core for our design and management questions.
Yes, in this slide it's mentioned that this share the rocket force data cache. Do you mean the registered file in the core, or is it some other data cache?
I do mean data cache, like L1 D cache.
L1.
Yeah, so L1 D cache. So we also, so if you actually look at your SHA-3 example, like the SHA-3 actually in the TripYard repository, it's actually accessing L1 directly. So I also have a here, so it can actually access L1 directly. So I do mean actually L1 cache. So the register, basically you can actually pass value through the source 1 and source 2 register here, and also write value to the destination register. So those are the, like the similar to the R-type instruction, those are the register interface. But it is a way to actually expose registers also to accelerator. So that's also coming very handy, right? You have some register you want to pass to accelerators instead of going through the memory map IO interface we'll also talk about in a minute, but here you can just pass the register directly to Excel. So that's why it means actually very tightly coupled. We get to actually leverage a lot of like things already presented in the CPU to do the management. Very good question. And so typically people like to separate ROC and the tile link. So one thing I mentioned here, we'll see a little bit more tile link later. But the ROC accelerator, besides accessing L1, we could also have a tile link node inside the ROC accelerator so that it can also participate in the tile link traffic. We'll see an example later, but it's not like either or, right? You benefit from the ROC, you can actually not attach to the like shared memory. You can still have a tile link node. Those are actually decoupled, so you can actually access either DRAM or like shared loss level cache. So that opportunity is still there, but we do benefit from the direct. I mentioned the page table walker access for virtual memory and also direct access. And like the question mentioned, like your name is Sp22?
Yeah, Sp22.
Sp22. Trying my best. I like to go to the L1 D cache or register directly. So that's another benefit of the ROC interface. So those are high level bits, but again, I'll point to some example that we'll see in a minute, just how different accelerators are actually using ROC interface. I also point to some repositories. Those are also very useful when actually think about ROC integration for tightly coupled accelerators. So before I move on, any questions, comments about ROC accelerators and the way we can use ROC to integrate accelerators into our system? Okay, yeah, so a good place to start is really like the SHA-3 example. You probably most focus on the data path in your lab, but to take a look at how it can be potentially integrated as a ROC interface into a RISC-V ecosystem. And I'll also point to some other examples. We actually have quite a few actually different accelerators designed with ROC interface, but more like combined ROC with tile link together, but you will be able to see the ROC connection, how we evoke it. So far we mostly talk about the ROC interface. As I mentioned earlier, this is mostly for tightly coupled accelerators. It just really treated accelerator as a beefy functional unit and have special instructions. And we use ROC instruction to actually invoke those accelerators. So this is one way of doing actually tightly integrated accelerator. But in today's system, right, in a lot of time, we actually have more like dedicated IPs or third-party IPs that we actually don't have control over. It's actually from a different design house, from a different company, and we like to actually integrate those IPs and also onto our system. So those IPs, instead of actually being in some sense like part of like ROC, what ROC really is part of the processor pipeline, those are actually more integrated as memory mapped IO or memory mapped accelerators, so that we can actually communicate or invoke those accelerators directly. So here we're going to talk about in the RISC-V ecosystem, how we actually use tile link to invoke it. Some of you, if you're more familiar with the ARM-based system, this is more like the AXI interface. People are using to integrate like different IPs or third-party IPs onto an ARM-based system. Those two are related, different, but at a very high level, when you think about what they are trying to do, right? You can think about like AXI for the ARM ecosystem and Talink for the RISC-V ecosystem. Right, so here we're transitioning a little bit, right? Instead of talking about ROC-based tightly coupled accelerator, we're more talking about actually memory mapped accelerators. Those are like loosely coupled accelerators, right? Instead of communicating or being invoked from CPUs directly as a special instructions, those are really communicating with CPUs through memory mapped registers, right? So those are how data is transferred. Everything is actually through the memory interface. So this is the key difference when we think about how accelerator or how IPs actually interact with the CPU system, right? So TileLink is basically a way to actually specify how those accelerators should actually participate, or those IPs, it doesn't need to be accelerators, right? How those IPs actually interact with each other and also interact to like some of the shared memory hierarchy, like the last level cache or DRAM. It can be also, we'll talk a little bit more with different protocols. You are familiar with ARM, like AXI also have different like levels of complexity. Some are coherent, some are not. Similarly, in TileLink, it also have different levels of complexities. But when we think about accelerator or IP integration, maybe some of the links would like to be coherent. Some of them is maybe just, oh, I throw data there and have a fence until the very end, I pick up the data, right? So those don't actually need to be coherent. Some need to be, some need to actually have a lot of bandwidth requirements. So we like to support the bursty traffic. So they're like, you can think of like standard AXI versus AXI Lite that we actually don't need to support the burst traffic. So those are like different caveats when we think about loosely coupled accelerator, how they are interconnected together. We'll talk a little bit more later. But here, the goal with the TileLink, at a very high level, and my mental model, I like to draw analogies. Actually, this is more like the AXI interface for ARM, but really support this kind of loosely coupled accelerators in our system with all the different IPs. So more specifically for TileLink, right? So this is in the RISC-V ecosystem, this is a way to actually provide memory mapped accelerators so that they can actually communicate to each other, communicate to CPUs, also communicate to memory, right? So this is again free and open source, used widely in RISC-V based system, in a lot of RISC-V based either like academic work or like even industry work, right? I think we spend a lot of time, most of the work, when we think about it, we spend a lot of time on the core itself, right? Like what are the special instructions? What are the like new functional units that we add? And you see a lot of time we just have this big box of TileLink as a shared bus there. But that's really the layer that actually specifies how things actually communicate or get connected with each other. It could be actually just between even you with multiple cores, right? We'll actually talk about even just with single core. There's actually a nice way of abstract how things actually talk to each other. But here in today's lecture, we'll be actually more focusing on how things are actually connected in a accelerator context, especially how data is actually shared between accelerators, coprocessors, for accelerators like inside the DMA engine here. So when people think about TileLink, right? So like I draw the analogy of TileLinks like the AXI protocol in the ARM world, right? Like AXI, there are all the different levels of complexities, like different ways actually supporting different traffic, right? TileLink has a very similar flavor to it, because when we think about system interconnect, right? Different system or different IPs actually have different functionality, bandwidth, performance requirement, right? So it just doesn't make sense to say, oh, we just design this protocol so that it actually works for all the IPs. So when we think about accelerator integration, I think one thing comes to mind always very important is also when we do like any specialized system, right? It's not only special or just specialize a core or the compute part. There are also a lot of opportunities to figure out what kind of system interconnect, how things actually connected together, right? So there are a lot of like subtle differences and also caveats actually like system architect need to choose when we think about the accelerator integration. So specifically, when we think about tiling, again, if you look at the code, there are like a lot of like very subtle differences here and there, but at a very high level, tiling actually specifies three levels of actually different communication protocols when we think about accelerator integration. If you're familiar with you spend like maybe just spend some time with the chipyard system, you'd probably see a lot of TL or tiling here and there and doing a lot of magic transactions here and there. But at a very high level, there are three levels or three different complexity or different protocols actually involved. So the first one is tiling uncached lightweight, or you see a lot of just TL UL. So U here means uncached. So this is, again, in my mental model, very similar to the way you actually think about an XC-Lite based protocol. So it supports data read and write from memory and also to memory, but it doesn't really support the bursty traffic. It's just very basic so that we can actually read and write. And memory is very light, so that's why it's lightweight. And it doesn't support the bursty traffic. That's why it's actually very similar to XC-Lite. And it also doesn't support coherence. So it basically provides a way to actually facilitate data transfer, which is a core reason that we actually want to, core functionality that we want to actually support our accelerator so that it can actually has a way to communicate with outside world. So it provides a basic functionality, but it doesn't have a lot of add-on feature to get more performance and maybe even more functionality, like coherence guaranteed here. So this is basically the basic. You have a very accelerator doesn't have a lot of bandwidth requirement. You probably also don't want to spend too much effort actually design this interface. Like the basic one, it actually works pretty well so that you can actually read write data from the memory and get the accelerator, keep the accelerator busy and get things running. So the UL is basically like the XC-Lite, something to start with. Like it actually works fairly well so that you can access memory. So there is a lightweight, right? There need to be a heavyweight one, right? Otherwise, it doesn't make sense. So that's UL, and then there's also H here, heavyweight. So it's still uncached. So whenever uncached, it basically not coherent, right? So we're not guaranteed coherence here. So when you see a U or uncached here, it's basically the data is not coherent. So like we are actually not guaranteed coherence. So you need to manually add fence there to make sure your data is actually propagated, but the data is not coherent. So it's still not coherent, but now it's heavyweight. So heavyweight, it has a range of different features. A lot of those are actually more CPU centric, like atomics operation is actually very CPU centric when we think about multi-core. Those are still useful, but for accelerators, it's really the bursty, supporting the bursty message for accelerator, because that if you are very bandwidth heavy, so instead actually essentially a lot of XC transactions, you want to actually support bursty traffic so it can actually amortize the cost of invoking actually bursty, not actually tiling transaction here, right? So again, it has like the prefetching and the atomic. Those features are more useful from a CPU point of view, but tiling not only for accelerator integration, it can also facilitate like more like multi-core environment CPU integration. But in the accelerator context, it's still not coherent, but it supports the bursty traffic. So again, if you folks are more familiar with the ARM model, this is basically more like a standard XC4, like it has a full protocol, not coherent, but actually has bursty message support here. So that's where the heavyweight comes from. Questions, comments, things you want to share? Okay. Okay, so this is more like, when you see like people talking about those things, like it's actually nothing too fancy about it. It's just different ways under describing what it supports and what can be done with different protocol. So we talk a lot about the U part, right? It's an uncached part, right? So if it has an uncached part, it must also have a cached part, right? So this is the coherence, like the highest level or the most complex level of support is actually the -C, the TL-C part. It actually supports the coherent transfers here. So it has all the, so everything is actually very inclusive, right? Okay, to more complex, in particular, I will talk about the detailed implementation in a minute, but the key differentiating factor is this is a protocol that actually support coherence. So it's more like, again, drawing the AXI analogy. This is more like the ACE, I think AXI coherence extension, right? So this is actually the one actually with additional traffic to actually propagate the coherence message. So this actually guarantees the messages, especially the stale data is actually updated properly if there are multiple writers. So this is actually the most complex one. I spent a lot of time actually trying to find the actually accelerator using the -C. So most of our example is actually caches. You spend time looking at the D cache or L2 cache designs in Chipyard. They are actually following the -C because it needs to be coherent. We actually don't have any design, at least yet, at least I haven't found any that's actually for accelerators using the -C, which kind of makes sense, right? Because when you think about accelerator, you don't want it to actually participate a lot into the memory, a coherence protocol that actually stall the execution, right? You want it just like run things as much as possible, and then just add fancier once the write is done, I just grab the data directly, right? So coherence is a nice feature, but it really depends on a good use case, right? In certain use cases can be useful, but in a lot of, at least the current accelerator design, we talk about loosely coupled accelerator, we just offload a big part of the compute there. We haven't actually found at least I haven't found a use case for -C yet, but this is like ACE, right? It's good to be there. If there's a need, that can also guarantee the coherence property when we think about accelerators. So those are the three types of tile link protocols. You can see there with like increasing complexities. If anything, I think just uncached, lightweight. UL is the basic version, support read and write, and then we get to heavyweight. Again, some like prefetching, like atomic features, but for accelerator, more like the bursty traffic is an important one. And then finally, the -C when we actually get to the coherent version. Any questions, comments, things also from folks online? Okay, so we talk about the three levels of complexities, right? Three different tiling protocols, and they eventually those protocols will be implemented as different channels there. So one thing you will actually see in any kind of tiling instantiation, right? So there will be agents, right? So agents are basically, we'll talk about different terminology, which can be a little bit confusing, but agents are basically the folks who either request traffic or the folks who are actually serving the traffic, right? So we'll talk about different terminology there, but then the channels are really basically the channels actually connecting the different folks. And we never, again, depends on complexity. Yeah, I guess. Yeah, well, actually, so this one actually has it. So depends on complexity. For most of the time, we're actually doing the UL or UH. We actually just do like A, like for request, sending out the address, and B for data, returning the data. So just like two channels actually involved in the communication. We only actually need to get to all 5 channels, A, B, C, D, E. You may actually see like TL.A, B, C, D, E, actually in a lot of the cache design that we have. Those are actually more for the coherence traffic. So for the basic one that we mentioned earlier, the UL and the UH, the rest of 2 channels, like we send the address and we get the data. So pretty straightforward. And the way you will actually see like the BCE, those 3 channels is actually typically involved in some coherence traffic there. So I already mentioned the terminology can be a little bit confusing, different like tiling use client and the manager to actually describe different agents in the system versus like AXI is more like using manager and the subordinate to actually describe the system. So let me first start with the AXI terminology, because the Tallink one, they actually also gradually converted to that one, which makes like easier to actually see that. So here in AXI terminology, manager is basically the one who actually requests the data. So manager has a ability to actually actively request data actually from like the subordinate device, versus the subordinate device is actually those ones who respond to manager's request and provide the data. So you can think about manager as like an accelerator or IP and a core actually sending request. And the subordinate is more like a memory, like a passive device actually respond to the request. So this is a terminology that we'll be using in this discussion. So manager is actually the one who sent the request. Subordinate is the one who actually receive the request. When you actually go through the tiling spec, it's a little bit confusing because they actually call the XC manager as a client, which kind of also makes sense. Like client has even higher priority, right? Client actually makes the request, right? But again, in tiling client is really just the manager who actually sent the request. And the tiling manager is more like, oh, I'm actually serving my client, so I'm actually respond, but it's actually more just subordinate. So this is the thing, you may actually find it confusing. Like for example, I'll show you an example later in tiling, we'll actually make a node, tiling node that actually actively sending requests. You actually do a make a client node. So it feels like client, but this is actually the one who actively sending request and receive and sending request and receiving data, versus memory is more like, I guess, the subordinate, which is actually supporting the data there. So again, so most of the time I will actually don't see the BCE, only channels are only show up in the cache design. So for most of the uncached design, most of the channels that we'll be using, the two channels that we'll be using is actually A and D. A sending the request, sending the address. D is actually responding the data. So it's also very easy to remember, I guess intuitive, like A for address, the A channel is for address, and the D channel is for data. So it's actually returning the data. So those are actually the fundamentals of like the terminology people are using when they describe tiling, different agents participating in the communication protocols, and different channels are used to actually to support the functionalities. And tiling is also a really, as the slide put it here, really the foundation of a lot of RISC-V based system, right? You will actually see different connections. When actually people label that, right, it may seem confusing, but again, whenever you see a U, it means uncached, not coherent. Whenever you see a C, it actually means cached. So when we actually see a RISC-V based ecosystem, it typically just involves all those different channels that are actually connecting different IPs together. Typically with a cache hierarchy, you see the tile C, tiling C connection, because we actually want to guarantee coherence. For at least most of today's accelerator, we have been actually seeing like uncached connections, because coherence is nice to have, but there are also overhead, right, to support all those traffic and performance penalty there. So we haven't seen a lot of adoption for the uncached protocol yet. Any questions, comments, thoughts? Straightforward, right? Just again, like doing assembly, right? Assemble different things together, but make sure we specify what we want to do, right? So it's a lot of this is really just making sure we are on the same page and we understand what we are trying to do. And again, different protocols have different complexities, and there's also different efforts involved. Ken?
I think on the previous slide, I just got like a slight non sequitur. I know that, to my knowledge, right now we don't really have like a DRAM controller within our ecosystem. So how exactly are we interfacing to like DRAM right now? Do we possibly use like a third party controller?
Actually, that's a good question. To be honest, I don't know how we actually interact DRAM controller in our ecosystem. They do in the chip, in the tiling specs, they do actually specify the tiling can also be used as an off-chip link, still basically using the uncached version, like the A and the D version that we're using. I actually don't know how we actually interact with, because we don't have a DRAM. I know like some folks actually did like a fake DRAM controller so that we can actually do some timing and simulation analysis. But Yeah, but it's still using the Tower-Link connection, but I'm actually not sure about how they actually replace the DRAM controller. Maybe you know after doing some digging. Oh, I should also mention for Tower-Link, because there are also some third-party IPs actually has their like AXI connections there. So what Tower-Link does inside the, I suppose, the RISC-V ecosystem, the bigger umbrella, there are actually Tower-Link to AXI converter available, and you can actually map this, like I mentioned, like spur-state traffic between AXI Lite to UL, or AXI standard AXI to UH, and ACE to Tower-Link -C. You can actually do those conversion. I didn't include that there. Like some folks last year they did the NVDLA integration. So NVDLA is a open source deep learning accelerator from NVIDIA. So that was actually using an AXI channel there. So there you can actually instantiate the Tower-Link to AXI converter, basically adding a wrapper there, and then so that AXI devices can also interact with the Tower-Link, participate in the Tower-Link design. So that's another example there. Question?
I have a question. So when we talk about the protocol levels, we talked about without coherence, there is need to manually ensure that data is propagated. And we also said that like basically uncached tilings are not coherent. But since they don't have any cache, we're doing direct access to memory. Is there still a need for you to do manual insurance of propagation?
That's a good question. So that's why the terminology is a little bit confusing. So it's called uncached, but you can actually still have your local memory, like scratch pad inside the accelerator. So we'll actually talk a couple of examples there. So it means uncached is basically more likely it's actually not coherent, but you could actually have, let's say, your hardware managed scratch pad in my system. I'm actually caching data locally because I don't want to do all my write to the memory system. So those writes that I'm actually writing to my local scratch pad, those are actually not visible to the outside world. So those are actually, so there are actually a lot of the designs where even we actually eventually will propagate data to DRAM, but we actually have some local buffers inside. And those, so here the protocol is more specifying those data inside your local buffer are not visible.
So you still have to deal with coherency. It's just that local buffer isn't called cache, so it's uncached.
Yeah, so it's uncached. So you still need to guarantee correctness in the end, right? So what they do is that you actually add a fence. They are eventually just like flush all your data, propagate that to the DRAM, and that's actually when the data eventually being visible. So there are also like that latency will actually flush your memory, your buffer to the, so that latency is also need to capture it, but instead of like every traffic, every write to my local either local cache or local buffer is actually visible. It's actually more like the explicit flush in the end to make my data visible. So that actually need to handle typically inside the device driver. So that's actually also need to be explicitly handled. Yeah, good question. Okay, so we already mentioned there are actually we'll see actually more examples, or this may seem actually too abstract at a high level. We'll see an example. So that will actually get things a little bit more concrete. But at a high level, I think the best way to actually see Tower-Link and how these things are actually connected is actually to look at those examples with pointers, right? So I guess I mentioned the SHA-3 example, accelerator you folks were doing is a good way to see the ROC interface. A lot of accelerators that we're designing here, especially at Berkeley, is actually more a combination of ROC and Tower-Link. So you'll see the ROC interface because it's actually very easy to invoke accelerators. You don't actually need to write specific device driver there. You can actually just treat it as a custom instruction. So we actually leverage that. You will see like 3 projects here as a protobuf accelerator, the Gemini accelerator. I'll actually have more details about the Gemini accelerator in a minute, and also the Huacha accelerator. So all 3 are actually more like ROC and Tower-Link combined. So we use actually ROC interface to actually invoke. Accelerator is actually a lot easier to set up the programming interface, but it also needs basically high bandwidth communication to share memory there. So they actually also instantiate Tower-Link nodes, as I mentioned earlier. All of our design are actually uncached because coherence is not that important overall, and for those very coarse grain computation. So I have 3 examples here, and interestingly, I guess one is the protobuf is actually doing a more lightweight design, and for both Gemini and Huacha, because we left the bursty traffic support, so we're actually doing a more heavyweight. But both are basically a combination of rock and taulic. And I guess the only one, well, not the only, I guess the one actually I find that actually seeing a lot is this actually the ISNIC, this interface controller actually inside FireSim. So that one actually more like a more standard like a memory mapped I/O device. So it doesn't actually have the rock interface. We just directly participate in the taulic communication as using the uncached interface there. So those are, I think, is actually a lot more intuitive to look at the examples to see how they are used under different scenarios. But you see when you actually design a coprocessor, design an accelerator, this kind of like, again, like all those accelerators are very different, right, in their internals, like how they actually handle computation, what they exactly did. But there are a lot of wrappers, or the interfacing logic can actually be leveraged across accelerator design. So those would also be fun actually when you think about your own accelerators here. Okay, so one more thing, I guess I already hinted earlier, right? So when you actually design and instantiate accelerator, always look for either make client node or just client node in general. So those are actually when the taulic node is actually instantiated. And again, the terminology is a little bit confusing. So client in taulic is actually the one who instantiates traffic, right? Just think about client is actually who make request, right? So here, when you actually instand the client, you can actually send a request to the memory system to actually get data. So there are, again, I guess mentioned earlier, take a look at those pointers, and there are a lot of shared wrappers across those designs and typically involved how we actually instantiate a taulic node in the design and the setting up different fields. So those will be the things that you look for. Client, again, related to the terminology, client is actually the one who makes the request in the taulic system. Okay, so we have talked a lot about like very, maybe a little bit also dry, like very abstract level of different communication protocols and in what scenario they are actually being used. Next, we're actually going to see an example and just how realistically and also what things are actually shared, right, across those accelerators, like really those wrappers, so that we can also design our own IPs. Before I move on, any questions, comments, or things folks like to share, both here and also online on Zoom? Okay, again, I guess I also mentioned earlier, this is a good time to also think about your project. Like we talk a lot about these complexities, but when you actually start your project, you're not starting from scratch, right? So even you ask those accelerator designers, they really don't start from scratch, right? They look at the code and there's always commonly used wrappers, right? You may actually configure different things differently. Your message may be of different size. You may have different control there, but there are always some actually common wrappers that you can actually leverage in your design. So let's look at an example to see how an accelerator actually can be integrated using actually both the rock interface and also the taulic interface in the system. Again, rock is very useful in thinking about programmability, how accelerator is configured, program invoked, and the taulic is very useful to actually think about accessing memory, right? So I mentioned like the three, the protobuf, Huacha, and the Gemini accelerators are both a combination of rock and the taulic. I'm using Gemini as an example, but you will find similar things in both protobuf accelerators and also the Huacha accelerator. And sometimes you look at the code, maybe even the same designer actually wrote both, or they actually also reuse the code. You can actually see a lot of similarities across them. So just a very high level like background, like we talk about, we're mostly talking about the wrapper logic in today's class, right? Like whenever we talk about accelerators, like what does the accelerator do? Like the functionality part, right? So here for the Gemini work, the functionality part of the accelerator is actually more doing a machine learning pipeline. It's actually processing like different deep learning layers, doing like either convolution or matmul or residual addition, ReLU, like all the typical deep learning functions, and then writing data to DRAM, and then being invoked for a next layer. So it's very representative. I mentioned earlier, when you think about a chunk of computation you like to offload to something very parallel and can do a lot of computation, you offload that. So Gemini, this example, Quadra is very similar, but more looking at the vector, and Protobuf is actually doing a lot of like data manipulation. So both have like quite a lot of computation going on. So we are using Gemini as an example. So Gemini, again, a lot of offloading here. And for today's context, we're mostly interested in first the ROC interface. Here is actually, you'll see similar things. This is basically how our CPU actually invoke accelerator here. And you'll also notice this, we actually also use a page table walker here so that we can actually directly use a virtual address instead of manually ping the data actually in our memory. So that also makes things a lot easier. So that the extended ROC interface, that's also like widely used in those accelerator design, actually leveraging the page table walker here. So that's the first part for the ROC part. And the second part is actually, so here our L2 is basically the shared loss level cache here, right? So those accelerators can also have access to the shared loss level cache through what we discussed earlier, the tile-link interface. And a lot of the logic actually encapsulated in this DMA engine, direct memory access engine. So this is also very common, like whenever you have the accelerator, typically you have a dedicated DMA engine to actually handle the memory transfer, right? So again, things are actually very modular. And so instead of actually touching all the pieces of your logic for tile-link connection, it's mostly actually all the logic is inside the DMA engine to handle the tile-link traffic. So those are the two things that are actually related to the integration we think about an accelerator here. Okay, so what are the steps when we actually use both ROC and the tile-link with an accelerator? Again, here we are using Gemini as an example, right? So how we actually get data. So mostly, again, any kind of accelerator, right? We get a chunk of data from memory, we do some computation, then we dump a chunk of data back to memory. So that's a typical processing. Again, you don't need to understand what Gemini does internally, basically fetch data, do a bunch of computation, throw data out, right? So that's basically any accelerator. But here are mostly just the typical steps that actually involved in actually using a ROC and a tile-link for an accelerator. So first, we mentioned the benefit of ROC is actually makes the software a lot easier, right? So instead of having to design your dedicated drivers, you basically have those like special custom RISC-V custom instructions. And whenever it's like CPU see those instructions, it actually goes, oh, those are the ROC instructions, similar to my R-type instruction, but actually with those fields is actually our ROC instructions. So here, the CPU basically directly dispatch those ROC instructions to the ROC accelerator. Here is basically the Gemini accelerator. So once the once the accelerator actually sees those instructions, it's completely up to the accelerator how they actually interpret those instructions, those data and the instructions here, right? So it could also encode some multiple different Gemini like the ROC accelerator instructions. So there could also be decoding logic in your ROC accelerator just to figure out like sometimes, like for example, a standard thing, sometimes we do some config, right? Configure like some parameters in our design. Sometimes we'll do actually to compute, that can be an instruction. And like a typical functionality, you also do like load and store, right? Those are also like basic functionality involved in any hardware design. So you still need to figure out your encoding, like the functionality that you want to do for the accelerator. So those are completely up to the accelerator designer, but CPU will faithfully transfer the data that you think you need to the accelerator, and the accelerator actually process those data and to figure out what exactly they want to do. So we mentioned earlier, so accelerators still need to have their own decoding engine, right? So we see those patterns, how I like to actually use those, what exactly I want to do. So here, again, using Gemini example, like we mentioned, just a very standard for accelerator, typically load, compute, store, right? You may have different version of compute, different configuration. So that's also configuration. That's also useful in the process, right? So, in my interpretation, in my decoding, this pattern is actually a load instruction. I like to actually I actually like to execute my load instruction. So here, whenever we talk about load, right? So here, everything is actually still a virtual address because it's actually tightly coupled. It's basically like doing a load actually inside the CPU, right? So inside the accelerator, again, another benefit of the ROC interface is you can actually instantiate, let's say, your own TLB, right? You can do a small TLB design to do actually virtual to physical address translation. And then you have a TLB miss, right? You haven't really populated your TLB entry. Remember the extended ROC interface that we mentioned earlier? The accelerator actually has access to CPU's page table walker, right? So here the benefit comes in. We can actually directly ask the CPU's page table walker to actually do the address translation. So this is actually a very important benefit, especially for like software development. This is just a lot easier, right? So you can actually leverage the CPU infrastructure. And if you're actually doing any design, I would also recommend you at least start from here because this is a lot easier to actually than like pinning your memory explicitly and doing like device driver support, right? So here, it's a load instruction. And let me get my address translated. I could actually instantiate my own TLB, so I can do some caching. If I have a miss, I can actually leverage the CPU's address page table walker to actually get me the physical address. Once I have the physical address, now is actually where tile link comes in, right? So tile link, I mentioned earlier, is a good way to actually pass in request to the accelerator, to the shared memory or even DRAM to actually, this really actually get to the send request and getting response part, right? So again, depends on the protocol. Most of the time we're using the uncached protocol, and then we basically send the request, wait for data through the address channel, and then wait for data. If we're actually using the cached, there's actually a lot more coherence traffic involved. You actually look at the cache design. But let's just think about the accelerator, very straightforward. We send a request and waiting for data, and then we configure like a bunch of metadata associated with the transfer. So that's basically actually the step actually involved when you think about the wrapper or the integration logic involved with integrating a third-party IP, right? So here we actually leverage both ROC and the tile link here, especially for ROC, the easy invocation, right? We can just directly invoke the accelerator, right, through the ROC interface. And also using the page table walker, actually, we can just use the virtual address directly and leveraging the CPU's page table walker to do the address and translation. And then finally, for block transfer, we actually use tile link so that we can access like the shared last level cache or even DRAM directly, right? So here is a very commonly used pattern in actually a lot of accelerator integration. Like I also mentioned earlier, we also have some examples there, right? So a lot of the patterns are actually basically like this. Again, you can configure things. There are still a lot of opportunities for innovation, right? I don't want to put it away like, oh, this is templates, just go do it. There's still a lot of opportunity for innovation, how you actually do your accelerator design, how you encode your design, right? How you interact with the system, how you design your state machine. There are still a lot of opportunities, but with this kind of like wrapper, it actually simplifies the design a lot. So that's a rough template of using Gemini, but this can also be generalized to any accelerators that want to use both ROC and tile link. Any other questions? Any questions? Comments? Things? So easy, right? This is so easy. Just design a bunch of compute, plug in, you have an accelerator talking to the outside world and get ready to tape out, right? So especially, I think, especially for like our circuit designers, I think like people tend to think, oh, once we get to the rest of the system, it's getting a lot more complex. Let's just focus on my innovation here. But the truth really is like there are a lot of templated design patterns that we can actually use directly nicely, and it's not that difficult to make our system a little bit more complex, but it has actually a lot of interesting features that we can run a lot more software on it. It make our system look a lot more interesting. So think about that, just a small delta really, like considering the efforts we need to do actually make our circuit a lot more efficient, more advanced, but having that small delta is actually what makes your overall system a lot more interesting. So with that, just a quick recap. I think we spent a lot of time talking about accelerator, a lot of innovation inside accelerators, but we want to use this lecture to give you a more system C perspective. And in the RISC-V ecosystem, two protocols are very widely used: ROC interface for tightly integrated accelerators and the Townlink interface for loosely coupled accelerators. They both have their strengths and their benefits, and we show a lot of examples that actually use both to actually simplify the accelerator design process. Again, this is really just a starting point. If you have any interesting ideas, I mentioned earlier, consider that delta to actually get to the system level that will actually make your system a lot more interesting. So well, I think we're almost time. This is the end of the lecture. But if you have any questions, comments, or anything you want to share, feel free to reach out. And well, good to see everyone, and enjoy the rest of the week.